Hi there. This is the demonstration video for CMP304 Artificial Intelligence. For this project, I built a handwritten digit recognizer using the MNIST database. Currently the neural network is being trained. It's being trained now. So the accuracy of the neural network on the testing inputs was estimated to be around 94.5%. Granted that the testing inputs are 28 by 28 pixels rather than this 280 by 280 pixel grid. But if you draw 0 here, it should say that it's a 0. Draw 1, it should say it's a 1. Draw 2, say it's a 2. Draw 3, it should say it's a 3. 4, a 5. Okay, that messed it up. Let's try that again. That's not a 6. That's 5. There we go. 6. That's a 7. That's a bad 8. That's a 8. Okay, it's not. That's a 8. Okay, this time. That's a 8. Come on. It's a 8. Yeah, there we go. The 9 is the least predicted one, but let's try it. No. 9. 9. No. Okay. Ooh, it might be because. Oh, there we go. Finally. I did it. Anyways. Oh. If you are having trouble, I've inserted this in the report as well. These are the uh, user inputs that were predicted right, and to like get a 9 predicted properly, for some reason like the line here should be smaller than usual. But other than that, most of the numbers get predicted quite accurately. It's the 9 that doesn't. Uh, anyways, now I'm going to try to explain how this entire thing works. The star you see the load mnis function. It loads the chunks of data. The MNIST data set that was divided into 10 chunks. It loads them into a vector of float, each of them, and those vector of floats are then pushed into a vector of floats called training data. This data is then used for training the neural network. So inside the model.train function, you can see that at first you evaluate what the data is. The evaluation, you go forward. Forward is the first layer is before that. Here, you add the two layers of the neural network. The add network is the input layer that has 784 input neurons. The add softmax is the output layer with the softmax activation function on it. So if we go back to in here, the first layer is the network layer which is the input layer. So if you go in the input layer and in the forward function, it calculates the output weight based on the weight, and then it adds the bias on top of that, similar to this equation over here. That's the weight plus the actual input plus the bias. So it does that here, and the next forward function that it goes to is the software activation one. And the software activation that's just the normal form of the software activation function, nothing changed in that. It's this one where the uh, numerator is the input vector and the denominator is the standard output vector, ranging from 0 to 1, and k here is the number of classes. In this project, there are 10 classes. After the model has been evaluated, it goes back to the training set and is stored in the model output, and then the deltas and the weights are calculated based on how far off the output was from the actual label output. So the last layer delta is calculated by subtracting the model output from the labeled output, which is then calculated in the cost function, which is the delta squared divided by 2, similar to this equation right over here. Then the deltas and the what's it called? The network.cpp, the deltas are calculated here, and the weights are calculated here. The weights are calculated the same way as the gradient descent, where you choose a small batch of randomly selected inputs, and then you calculate the deltas for that, which will estimate, it's an estimation that it will be equal to the normal cost function. And then you return the cost function, which is then displayed on the console window right over here. It's done for 10 epochs, which means the train data is passed 10 times. After the data is trained, I test the data using the label, use the testing data, and the evaluation function, and the accuracy is calculated by the number of tests run divided by the number of correct tests multiplied by 1,000. It gives us the accuracy, and now the user can input their own digits to be evaluated by the neural network. It goes the same way, except here when the digit is inputted, I calculate the average of all the three RGB values, divide them by 3, that's the average, divide them again by 100, and then normalize them, then push them into a vector, and this vector gets passed into the evaluate function, which returns a softmax activation probability distribution. And the probability distribution goes into the max element, which calculates the largest or the highest element in there, and it returns the index of that element, which then says the prediction. That was my project for CMP part 1 of this module.